Good morning, everybody. It's my pleasure today, an honor, to introduce Professor William Phillips. Professor Phillips is a senior fellow at NIST, the National Bureau of Standards in Washington, D.C., and a professor of physics at the University of Maryland, College Park. He has made groundbreaking contribution to the field of laser cooling of atoms and the study of quantum phenomena in general. And for his work, he was awarded the Nobel Prize in Physics in 1997 for the development of methods to cool and trap atoms with light, a prize that he shared with Stephen Chu and Koen Tanuji. As I learned for his Nobel lecture, Professor Phillips started thinking about cooling atoms with laser already as a postdoctoral fellow at MIT. Bill graduated from MIT in 1976, and he remained for additional 2 years as a postdoctoral fellow before joining NIST. In 1978, as a postdoctoral fellow, he got interested in an experiment performed by Ashkin about trapping atoms, and that experiment really gave a dramatic demonstration of the mechanical effects of light. He was also influenced by another paper by David Wineland about laser cooling of ions, and he decided to try it with atoms. Only 4 years later, in 1982, he published the first paper outlining the cooling of neutral atoms. And the process he used, now known as the Zeeman slower, has become one of the standard techniques for slowing atomic beams to close to absolute zero. At NIST, Professor Phillips initiated a new research program on laser cooling. He founded NIST Laser Cooling and Trapping Group, and he was a founding member of the Joint Quantum Institute devoted to the study of quantum coherent phenomena. Again, as I learned from his Nobel lecture, Professor Phillips started doing laser cooling because he was determined to do better atomic clocks, and indeed he succeeded. Atomic fountain clocks, based on the work of his group, are now the primary standards for world timekeeping. I told you just about one of his awards, the Nobel Prize in Physics, but he has received numerous recognitions. He's a fellow and honorary member of the Optical Society, a member of the National Academy of Sciences, of the Pontifical Academy of Science, and the corresponding member of the Mexican Academy of Science. In closing, let me mention that Professor Phillips has been an advocate for science throughout his career. For example, he was one of the Nobel Prize winners signing a letter to President George Bush in 2008, urging him to reverse the basic energy science budget that they had signed at the time. And later on, he was one of the people, again, Nobel Prize winner, signing a letter to President Obama asking him to support research in clean energy. Thanks for being with us, Professor Phillips, today, and share your thoughts about the second quantum revolution. The floor is yours. Thank you very much.
Thank you, Giulia, for that kind introduction. As you've heard, I'm part of the Laser Cooling and Trapping Group at NIST and the Joint Quantum Institute that is a joint between the University of Maryland and NIST. And here is the Laser Cooling and Trapping Group. Gretchen Campbell is now the leader of that group, and I'm so pleased with her leadership and the opportunity to work with all of these wonderful people over the years. Laser cooling, when it started, we had no idea that we would be dealing with quantum information and the kinds of things that I'm going to be talking about in the context of the second quantum revolution. But if there is a second quantum revolution that we're in the middle of, you might ask yourself, well, what was the first quantum revolution and what was it a revolution about? Well, I've indicated here that the thing that preceded the first quantum revolution was classical mechanics, the kind of thing that Galileo and Newton taught us about. And the first quantum revolution taught us about things like atoms and molecules. The wonderful things that we heard from Ben Feringa about molecules, you can't understand what's going on in those molecules unless you understand quantum mechanics. So what was quantum mechanics revolting from, so to speak? Well, it was, as I've mentioned, the classical mechanics that people like Newton and Galileo and du Châtelet gave us beginning in the 17th century. And the thing that I want to emphasize here is that this was a revolution not just in the intellectual understanding of the way the world worked, being able to understand, for example, planetary motion, falling objects, the kind of predictability, the fact that you could understand when and how and why things were going to happen mechanically, led to a different kind of revolution, what we call the Industrial Revolution, basically a technological revolution that gave us, based on this scientific understanding, things like engines, trains, steamships, and all kinds of things that were important to society from the 17th to the 20th centuries and are still important today. Without that understanding of classical mechanics, we wouldn't have things like automobiles. So classical mechanics explain the behavior of all sorts of ordinary objects. Macroscopic objects, billiard balls, which physicists are very fond of talking about, planets, steam engines, these were the kinds of macroscopic objects that classical mechanics allowed us to understand. Quantum mechanics, which was born at the beginning of the 20th century, gave us an understanding of submicroscopic objects, atoms and molecules and electrons. And here, on that submicroscopic level, the rules are different. The rules that govern the behavior of planets and billiard balls and steam engines are not sufficient to understand what goes on at the atomic and molecular level. So the kinds of things that people like Einstein and Bohr and Schrodinger and Heisenberg and Curie taught us about changed the way that we think about the physical world. So it was very definitely an intellectual revolution. It was really profound because the predictability that we had gotten from classical mechanics was gone at the microscopic level. It turned out that one could not predict what was going on. Heisenberg famously gave us the uncertainty principle that emphasizes the lack of predictability of what happens at the quantum level. But as with classical mechanics, quantum mechanics was not only an intellectual revolution, it was also a technological revolution. The 20th century was changed in a really profound way by the kind of technology that quantum mechanics gave us. I'm talking to you via a computer and via a network that wouldn't exist if it weren't for quantum mechanics, because quantum mechanics explains the behavior of electrons. Electrons in, for example, semiconductors. And without an understanding of how electrons behave in materials like semiconductors, we wouldn't be able to build computers and smartphones. We wouldn't have optical communications. We wouldn't have CDs and DVD players. We wouldn't have the kind of robots that Ben Feringa was talking about on the macroscopic level, that are a kind of an analog to the kind of robots that he's building on the microscopic level. We wouldn't have any of those amazing things that, in a sense, define what everyday life is about. So what was the revolutionary thinking, the intellectual revolution that resulted in this change? Well, one of the most fundamental things, one of the most important things about quantum mechanics is the understanding that particles are waves, that electrons, which had been discovered some years earlier at the end of the 19th century and were thought of as little charged particles, that these things actually behaved like waves in addition to behaving like particles. Furthermore, light, which in the 19th century was shown to be a wave, turned out to also behave like a particle. Everything, in fact, behaves like both a wave and a particle. De Broglie gave us this notion for particles, telling us that the wavelength of the wave behavior of a particle was equal to Planck's constant, a pretty small number, divided by the momentum, the mass times the velocity of that particle. Now, here's why quantum mechanics is so important at the submicroscopic level, and why we can get away with ignoring it typically at the macroscopic level. If you ask about a billiard ball rolling across a billiard table and ask what is the de Broglie wavelength of that thing, it's 10 to the minus 30 meters. That is an almost unimaginably small number. It's 10 to the 15 times smaller than the diameter of a nucleus. It is so small that it simply doesn't matter. On the other hand, if you ask what is the de Broglie wavelength of an electron in an atom, it's 10 to the minus 10 meters, which is the size of the atom itself. So it's really important. You cannot ignore the wave-like nature of an electron when you're dealing with an atom or with a molecule. Now, the wave nature of matter is really cool, and it's responsible for a lot of the things, the technological things that we have gained from our understanding of quantum mechanics. But there's a lot more stuff to quantum mechanics, and some of it is pretty weird. Think about an electron. We often think of an electron as a spinning top. Now, if I have an ordinary spinning top, I can turn that top so that it points, its axis points in any direction. But that's not true of an electron. If I define a particular axis and ask what direction is the electron pointing compared to that axis, there are only two choices. It's either pointing along the axis or opposite the direction of the axis. In other words, the direction of the spin is quantized, it's discrete. A lot of other properties like energies are quantized. They are discrete at this microscopic level. But this idea that an electron can only point in one direction or another leads to all sorts of wonderful features that we're going to talk about in just a moment. But just in case you're thinking that maybe you understand a little bit about what I'm talking about quantum mechanics, and Feynman famously said no one understands quantum mechanics. Think about this. The electron is spinning. The size of the electron, both theoretically and experimentally, as far as we can tell, is zero. How does something that has zero size spin? I don't really understand that, but it does. And we've done all sorts of experiments to verify that it's spinning, that it has angular momentum. But here's something about this idea that the atom, that this electron can be only up and down relative to some axis at this. It can also be both up and down at the same time. In other words, it can be in what we call a superposition. If I put the electron in a superposition of being in both up and down, if I measure it, it's going to be either up or down, but it's impossible to predict which one of those answers it's going to be. But here's the important thing to understand. Before I measure it, it's not that it's in the up state or the down state, and I just don't know yet because I haven't measured it. It's really, in a very profound sense, in both states at the same time. And it's only when I measure it that it brings into reality the fact of the atom being in one state or another. It's not really in either state before I measure it. Well, there's all kinds of weird things about quantum mechanics. The fact that the vacuum isn't empty, one of my favorite features about quantum mechanics that is so weird. But how do we understand this? Well, the fact is, I don't think there is any way of understanding how something can be in two places or in two states at the same time. But here is an attempt to illustrate that. Look at this drawing of a cube, which you've seen probably any number of times. One of the problems with this cube is that if you look at it for a little while, you see that you could think of that cube as being in two different states, that this face, the one I'm outlining here, is the one forward, or that this face is the one that's forward. Now, before you look at it and your brain sort of seizes upon one or the other of these things, you might say that this picture is in both states at the same time. It's only when you look at it that it, in a sense, collapses into being this or that. Well, I want to emphasize that this is not a real analog to superposition, because there is no classical analog, but it gives you a little bit of a feeling of what's going on. Now, I want to talk about something else, entanglement. Now, I'm always worried when I give a talk like this for a more general audience, because the specialist will understand that entanglement is just a more general form of superposition. But for me, it's even more weird than the idea of superposition. What is entanglement? Imagine I've got two particles, and each of them is like an electron. It can have its spin up or its spin down. But I've made a state of both of these electrons at the same time. And the state is a superposition of the first electron being up and the second electron being down, with the first electron being down and the second electron being up. Now, if I was to ask, is electron 1 up or down, or is electron 2 up or down? Well, that isn't a question I can answer until I measure. And if I measure electron 1, I have no idea whether it's going to be up or down. But if it's up, then electron 2 is going to be down. Before I measured electron 2, if I hadn't measured either electron 1 or electron 2, I'd have no idea whether electron 2 is going to be up or down. But the point is, the fate of electron 1 is entangled with the fate of electron 2. And what that means is that it is impossible to describe what's going on in this system of two electrons by only thinking about what happens first with electron 1 and then thinking about what happens with electron 2. Their fates are entangled. I have to think of both of them together. A lot of times we like to think about what happens if we start with two electrons together and they're entangled like this, and then I send them to two different places where I might detect them. Before I detect them, as I mentioned, I don't know whether the state is going to be up or down, but as soon as I detect this one, set its state into concrete, so I've got a concrete block here to show that, then immediately over here, this electron is going to be down. And it doesn't matter how far away that other electron is, somehow or other, it immediately knows that it's supposed to be down as soon as this one's been measured. And that freaked Einstein out because he understood correctly that you can't have information transmit faster than the speed of light, and it appeared that it did. Well, in fact, there is no information. Everything is fine relativistically. It's really true, even though Einstein didn't like it. And I also want to have a caveat that I've cheated you a little bit in the explanation, but we can talk about that in the questions if you like. But here is sort of a classical version of the entanglement thing. Now I've got two of these boxes. Now, I don't know about you, but when I look at those boxes, I tend to see them both either this way or that way. So in a certain sense, the fate of these boxes that could be either this way or that way, those fates seem to be entangled. But again, there is no good classical analogy. Now, here's the point that I want to make. The first quantum revolution was mainly about the wave nature of electrons. It wasn't about these more deeply weird features of superposition and entanglement. Everybody knew about those things, but in general, people didn't think that they were that important. And in general, the technology didn't use them. Part of the reason the technology didn't use superposition and entanglement was we hadn't actually gotten good enough about making really good semiconductors that superposition and entanglement would survive. And the other thing was that people really hadn't thought deeply about what the meaning and consequences of things like entanglement were. The second quantum revolution is a revolution that puts that weirdness to work. So part of this second quantum revolution is a kind of a marriage between two of the most revolutionary developments of the 20th century, quantum mechanics, which we've been talking about, and information science. Now, quantum mechanics was wonderful. It really changed the way we think about the physical world. It changed our philosophical approach to the physical world. Information science changed the way we think about thinking. We now have machines that do something that before the 20th century, we thought was the province of individuals like ourselves that can think. And now we have machines that can think. And what the quantum information revolution does is bring together these two 20th century sciences and technologies to a new 21st century science and technology that we call quantum information science. And here's one of the things that I find so fascinating. This quantum information science, which is now just coming to fruition in the 21st century, is really changing information science in an astounding way. Quantum computers, a dream that really is starting to become a reality right now. Quantum computers are more different from today's computers. The computer that I'm working on looks just like this one. They are more different from a computer like this than this computer is from the ancient abacus. That is, the philosophy that underlies a quantum computer is more different than the philosophy of this modern computer is from this ancient abacus. Why is that? Well, let's remind ourselves of the way computers process information. They process it in bits. You remember that Ben Feringa talked about the state of these molecules as representing bits, 0 or 1. It could be spin up or spin down. Anything that has the possibility of being in two different states, like a transistor being turned on and off, or a magnetic material being magnetized in one direction or another, a CD burned in a spot or not burned in that spot. These are all classical bits. And one of their wonderful features is that it's very clear whether they're 0 or 1, whether they're up or down. Quantum bits turn that idea on its head. Quantum bits imagine that the system, like say an electron, could be in a superposition of 0 and 1, a superposition of being up or down. Well, that sounds like a disaster because unlike classical information where you're really sure that the bit is 0 or 1, here you have no idea what it's going to be when you measure it. Why is this any good? Well, here's why. Think about a classical register of 3 qubits. I have 3 classical bits. Here's 1, 1, 0, 1, that's 3 bits. That's the binary representation of 5. This classical register could have stored any number from 0 to 7. Let's think about a quantum mechanical register of 3 qubits. Because it can be in a superposition, it can store all of the numbers from 0 to 7 at the same time. That is, it could be this superposition of 8 different numbers. The result is that if I've got a classical register, I can store 1 n-bit number. If I've got a quantum mechanical register, I can store 2 to the n. Okay, this is 2 to the 3, right? But if I had 300 qubits, 2 to the 300 is a number that is bigger than the number of particles in the entire universe. That exponential scaling is one of the things that gives quantum information and quantum computing its power. And there are some important problems that benefit from this exponential scaling. One of them is factoring. It's easy to multiply 2 numbers together to produce some other number. But if someone gave you this number, you would have to work for quite a while with a calculator probably to figure out what the factors were, whereas any elementary school student could easily multiply those 2 factors together. The fact that it's easy to multiply and hard to factor, even though they're just the inverse operations of each other, is at the heart of what is known as public key encryption. When you buy something online and you give them your credit card, that credit card is protected by public key encryption that relies on the fact that it's easy to multiply and hard to factor. But here's the deal. This genius, Peter Shor, figured out how you could use a quantum computer to factor numbers and turn that problem into an easy problem. From a computer science point of view, this was amazing. You took a problem that is defined to be a hard problem, meaning that it becomes exponentially more difficult as the problem becomes bigger, as the number that you're trying to factor becomes bigger. That's a hard problem in computer science. And you change that into an easy problem by changing the hardware that you use to do the calculation. Now, we don't have quantum computers that are big enough today that can factor interesting numbers, but we're on the route to doing that. And this is one of the reasons why so many people are so interested in quantum computers, because it could break all kinds of codes that protect things like diplomatic secrets and financial information. And so people are spending a lot of money on quantum computers. Okay, let's see. People have written science fiction about quantum computers, but quantum information isn't science fiction. There's a lot of application to quantum mechanics, to studying the kinds of things that we heard about from Ben Feringa. For example, one of the things that's really hard to understand is out of equilibrium. And as Ben told us, out of equilibrium is really the essence of the really important things that go on in chemistry. And it's really hard for classical computers to calculate that kind of problem. And quantum computers can do it, and quantum simulators can do it. And I haven't really talked about what the difference is, but we can talk about that in a moment. But think about this. There are things that we don't even understand about quantum computing. Here's a quote from Michael Friedman, who's a Fields medalist, sort of the mathematical equivalent of a Nobel Prize. And what he said was that if you had a device, a physical device, he's thinking about a quantum computer that could solve a certain kind of problem. And we don't know that quantum computers can solve those kinds of problems, but it looks like they're close to solving those kinds of problems. He said, if you had such a thing, that it would supersede intelligent, even artificially intelligent proof finding with an omniscience not possessing or needing understanding. I don't even understand what that means, but it sounds beautiful and amazing. And it's one of the reasons why I really want to make a quantum computer. Now, here's another killer app for quantum information, secure data transmission. Think about how ordinary classical communication works. The source, A, who we call Alice, wants to send some message to B, whom we call Bob. And I like to anthropomorphize Alice. So here's Alice Cooper and here's Bob Marley. And the issue at hand is that there may be an eavesdropper, whom we call Eve, who taps the line between Alice and Bob. And this is a fundamental problem in the security of information. And even if it's encrypted, you have the problem of the possibility of decrypting it, maybe with a quantum computer. What if you send the information not as classical information, but as quantum information? So let's imagine that Alice is a good quantum mechanic, and Alice creates an entangled state, the sort of thing that we talked about before, where the spin could be up or down, but there's two spins, and their fate of being up or down is entangled one with the other. So what Alice does is keeps one of the qubits, number one, no idea what it is until it's measured, and sends the other qubit over to Bob. No idea what it's going to be until Bob measures it. Now let's say Eve tries to intercept the qubit. Because of something called the no cloning theorem, which says you cannot make a copy of an unknown quantum state, Eve cannot make a copy of this state, measure it herself, and send the other copy to Bob, sort of intercepting Alice's transmission without it being evident to Alice and Bob if they later compare some of their results. So Eve is out of the picture because it becomes tamper evident that Eve is trying to do something. So what Alice and Bob do is they take some fraction of their transmissions. Alice says, do you get that information? Bob said, yes, I did. They've both measured it. And because they're entangled, they both know what it is. And they can say this publicly, that they both got the information. But they don't have to say what it was because they know and nobody else does. In this way, they can create a secret key that allows them to send any information that they want. And people are doing this at NIST, at my organization. We can send this key so fast that we can live stream video in quantum key. Now, what are these qubits that we're sending? Well, one of the favorite ones is photons, single particles of light. That's what we use to do communication. Single ions in a vacuum are one of my favorite ones. People like Dave Wineland, whom you heard about, who inspired me in the early part of my career, he's one of the pioneers of using single ions and the spins, say, of those single ions as qubits, as bits of quantum information. You probably heard about Google making a quantum computer that could do things that classical computers couldn't do. Those use superconducting circuits. They sort of break the general rule that these things have to be submicroscopic. These things are relatively large, microns in size. Single isolated atoms, these are the kind of things we work with in my lab. Quantum dots and more things. People all over the world are doing these kinds of things. So here's a kind of a simplified version of what an atomic qubit might look like. In my lab, we often deal with alkali atoms where we've got a nucleus that's got some kind of a spin, and we've got one valence electron that has some sort of a spin. And there are states that involve the electron spin and the nucleus spin being lined up in the same direction, and states that have a different energy where they're lined up in different directions. And we can create superpositions of these things. We call one of these states 1 and one of these states 0, and we can create superpositions of these two different energy states, and that becomes the qubit for our quantum information. So let me show you a movie that is sort of a dream of how we would like to make a quantum computer using these atoms. We have the atoms set in an array called an optical lattice, which we make with beams of light that trap the atoms in microtraps, many, many microtraps, and we can put the atoms where we want. And now we come along with a laser beam and pick it up. And this laser beam is often called an optical tweezer, something that Art Ashkin, who you heard about in the introduction from Giulia, got a Nobel Prize for. We pick the atoms up using optical tweezers. We bring them together so that they interact. It's important to make them interact to do the operations that a quantum computer would do. The actual calculations involve allowing these atoms to interact, and then we can put the atoms back where it belonged, having done something to the atoms. We put it back into memory, or we can pick up a whole group of atoms together and have them interact with another group of atoms. Why are we doing this? One of the reasons is that one of the problems that we have with these atoms is something called decoherence, the fact that the atoms talk to their environment. And so there are errors that happen in the computation. These errors hardly ever happen in classical computers, but in quantum computers, they're going to happen all the time. We have to do error correction. And when we get a whole group of bits together, there are processes that we can perform called error correction routines that allow us to fix those errors. So even though these quantum bits are really fragile and are subject to all kinds of errors, we can fix that by using arrays of qubits and doing the right kinds of operations on these qubits. So at the very end, then we are going to take these qubits that we've been looking at, and we're finally going to measure what the state is. So this is another important feature. We must not ever look at what the state of these qubits is until the very end. Because if we look at the state, it collapses this wonderful superposition that we have to be so careful to maintain. Well, when are we going to have these computers? We already do have things like you may have read about from Google, from another company called IonQ, Chris Monroe in my laboratory, Dave Wineland in, not in my laboratory, but at the JQI, where my laboratories live these days. Dave Wineland at the Boulder laboratories of NIST are making small-scale quantum computers. These things are useful for doing all kinds of interesting small quantum mechanical problems, just on the verge of being doing things that cannot be done with quantum computers that are really interesting, that people care about. The thing that Google did was a problem that nobody cared about, but it demonstrated the ability of quantum computers to do things that classical computers couldn't do. How long is it going to take before we have a big computer that can factor numbers? I don't know. It's going to be really hard, but it doesn't seem that there's anything fundamental that keeps us from doing it, just that it's really hard. It's probably going to take at least 20 years, maybe 50 years, but we're already using quantum information devices to simulate the behavior of systems that are too complicated to calculate directly. And this is the great advantage of these quantum information systems, that our classical computers are simply incapable of calculating what's going on in these quantum systems because of this exponential scaling. But the quantum systems have the exponential scaling baked in. And so they can address these kinds of issues. Non-equilibrium physics, the kind of thing that Ben Feringa told us was so important, just molecular structure, which is so important to the kinds of things that are designed in the kinds of things that Ben was talking about. And already just the nature of the thinking about quantum information has affected classical computations, so that we have quantum-inspired classical computations that are working better than anything we had before. Well, there's lots of other things. I don't have time to tell you about all these things. I talked about decoherence and error correction and quantum-inspired solutions, but the key thing is that because of this weirdness finally being put to work, we are in the midst of what I really think is a new quantum revolution, both intellectually and technologically, and it has just amazingly exciting prospects, and it really looks like a bright future. Thanks very much.